Sometimes it's instructive to see a circuit put together piece by piece, not just the components and the design, but also seeing the signal change from one end to the other, a signal processing change transforming the signal. We go from our input in our amplifier to our output changed voltage. For the common emitter amplifier, my favorite one, obviously. And also, at viewer request, I now present you an oscilloscope's journey through an amplifier. So I have here a 2N2222A NPN transistor with heatsink. I have a potentiometer, a 10K potentiometer that will serve as our volume knob. On the low end, it's reading 4.1 ohms, and on the high end, it's reading 9.32. Pretty bad tolerances, but pretty cheap potentiometers. As for resistors, these are the same ones from the other day. The first bias resistor is 1197 ohms. The second bias resistor is 270 ohms. The collector resistor is about 68.2 ohms. And the emitter resistor is about 18.3 ohms. The three capacitors I'm using are 10 microfarad ceramics. I don't have a way to measure the capacitance, so we'll just take their word for it. So let's assemble our circuit piece by piece. The first thing we need is our signal. So I'll plug the signal into the board here, and I will generate a 1000 hertz, 1 kilohertz, so that's in the human hearing range, sine wave, 1 volt peak to peak. Let's go ahead and measure that. Let me turn off the green for a moment. So if I turn this up to 500 millivolt divisions, so you can see what's going on, here's 0, so it goes up and down to plus or minus 0.5 volts. So there's our input signal. Now the first thing I want to show you is the volume knob. So I'll go from signal into the potentiometer into a random 1000 ohm resistor, doesn't matter, to simulate a load, because the volume knob acts as a voltage divider. So out of that 1K, back to the ground of the signal. The potentiometer acts as a voltage divider with the rest of the amplifier, the load. So 1K is just, it's there, so there is a load to divide with. So if I measure the input signal, and then alongside that, I measure the voltage that the load is seeing as its input. I turn on the green here, set its height to also 500 millivolts. We can see that the signal's diminished. If I turn the potentiometer down, then we basically get the signal back. In fact, let me make this taller so you can see it a little better. The potentiometer is currently down at its minimum. If I turn it up, all the way up, we get a signal that is probably quiet enough to not be heard. On a real speaker, a normal one, if you put it very close to your ear, when the volume knob is at the bottom, you'll probably still be able to hear a teeny tiny piece of the audio. But this is the volume knob. Up, down, and that's all there is to it. And now I'm actually just going to get rid of the volume knob because I won't need it for this demonstration. The emitter resistor and the internal resistor here provide more than enough to make sure this thing doesn't blow out. So let me just remove all of these and we'll build the proper circuit. So I will be using as my amplifier power supply the 9-volt wall wart, which if I measure that, should be the same as before, about 9.18 volts right now. So it is indeed roughly 9 volts. So the first thing I'm going to do is join the grounds. Common ground, negative side, the negative of the signal with the negative of the wall wart. So now it doesn't matter which side we plug it into. I'll go ahead and permanently have the yellow here as the input signal as a reference. So there's our input signal again, and I'll turn off the green just so it's not distracting right now. So let's connect up pieces of this circuit. The first thing I'll do is connect the bias. So from the 9-volt power supply into the first bias resistor, out of the first bias resistor into a trace we'll just call the bias point, where everything joins up, then continuing on into the second bias resistor, and from there to the negative. So now we have an active bias. Let's measure it. So the voltage being seen at the bias point is as we would expect. This is millivolts, so about 1.693 volts. About 1.7 is what we wanted. So there we go. So the bias is working. Now I will connect the amplifier portion to the transistor. So from power again into the collector resistor, from the collector resistor over to this other trace, and this is going to be basically the output signal there, and then from that output into the collector, which is tricky to get to because somebody put a big old clip in the way. Then I connect the emitter or try to, there we are, connect the emitter into the emitter resistor, and the emitter resistor to the shared ground. Nothing's happening, of course, because there's no base connection. So I will connect the base point to the base of the transistor. So now let's measure voltage again. If I measure the voltage of the output, we will see it's at about 5.5 volts. So we had something like 9.2 from the supply, and then we had about 1.7 being removed from that. So 9.2 minus 1.7 is 9.0 minus 1.5, is 8.5 minus 1 is 7.5. So 7.5 is about how many volts of room we have to work with. So it's 4 some volts-ish is the midpoint, plus 1.7 to get back up to 5 some volts. So this is our roughly proper midpoint. So between 1.7 and 9.2, 5.4, it's about halfway. So that's our quiescent voltage working properly. So now let's connect the signal. So now let me connect the green probe to properly measure the output. So I'll connect that to ground and this to the output signal, which right now we see is way up here. So let me shrink both of these that far. So if I pause it, these divisions are now 2 volts. So the signal is pretty small, as we know. The bias point is up here. 2 volt division, so here's 0, 2, 4, 5-ish, somewhere in there. So there's our quiescence. And now I will connect the signal. So we'll go from the positive signal into one of the capacitors in series. So out of that capacitor, and that just into the bias point. And all of a sudden, we seem to have a signal up here, don't we? So this signal, and you can see it's inverted. If I bring this one up, just so these are different voltage ranges now, but so you can see it. We have, here, there we go, smooth that out. You can see, as we know, it's inverted. The input signal and the output signal are inverted because this is essentially a live NOT gate. It's a NOT gate with a varying voltage rather than just high or low. So the common emitter is an inverting amplifier. This doesn't matter because it doesn't matter which way the diaphragm of the speaker is pushing. It only matters if we're digitally processing this or we're mixing inverting and non-inverting amplifiers. And even then it might not matter depending on how you hook it up. But this just changes the direction of the wiggling, and that's going to be imperceptible. So now, if I put these back, so this is both 2 volts. So this is the original signal, and this is the amplified signal. These divisions are 2 volts. So you can see the peak voltage, the peak-to-peak voltage, is higher for the amplified signal. We have gain. So now, let me show you something else. I'm going to connect the output through the capacitor that removes the bias. So I'm going to take out this probe, and I'm going to connect from that output to a capacitor, out the other end of the capacitor, up here to a random low-value resistor. I believe it is 100 ohms. Yes. And then out of that 100-ish ohm resistor, I'll just use this ground because my wires are stretching. So now what we have is a load, a 100 ohm speaker, which is really, really high. Even headphones are like 32 ohms. But the point is it's a load that we can measure against. So if I look at the voltage that the load is seeing on my green probe, there we are. Let me stretch it up a bit. So now we have 500 millivolt divisions, and the green signal is vastly diminished because 100 ohms is a lot. That 100 ohm resistor is demolishing this signal, but it's still higher. You can see it's still higher. It's the same inverted signal, and it's down at 0. See? The capacitor removed the bias, and our speaker is terrible because it's incredibly high impedance, but you get the point. That capacitor removes the bias. So let me undo that. Now that we've seen we can remove the bias, I want to have the full undiminished signal. So I will go back to measuring the actual biased output. So let me bring it back down here. So here they are at 2 volts again. The divisions are 2 volts, and you can see the nicely amplified signal. But I'm actually going to turn off the yellow for a moment. And I want to show you the difference. If I shrink this down to 5 volts, so we can see each division is 5 volts. And this has a span, well, let me bring it back up again. The span is about, so this is 2 volts, so about 2, 3, maybe 3.5 volts peak to peak. There you go. So let me bring it back down to 5. Now, do we recall that we can put a capacitor in parallel across the emitter resistor to give a path for the AC to follow and avoid that resistor, colloquially speaking? Well, let's do that. I will connect from one side of the emitter resistor to one side of this capacitor, and the other side to the other side of the emitter resistor. And it may be hard to see. I'm going to take it out and in and out and in. Perhaps it will be easier if I do freeze frame, bring it down a bit, make it taller a bit. So right now we're here. So I'm going to take the capacitor away and unpause. Watch it get smaller, smaller. I'm going to put the capacitor back in and watch it get bigger, bigger. This is kind of hard to see, so I'm going to use a trick. So let me actually shrink the time so it's kind of a bar, right? So you can see this bar is about that high. Now, if I take the connection to the capacitor out, do you see the bar goes down in comparison? It goes back up and down and up. Do you see it? There you go. So that is the process of using the capacitor across the emitter resistor to get some of your gain back. Basically removing 1.7 or so. It doesn't work out exactly that way, but kind of does. To get some of your headroom back, which causes your gain to go up as well. That can introduce distortion. Depends on if you pick the right capacitor according to that 1 over 2 times pi times the lowest frequency you care about times the impedance of whatever's coming next. That whole video I did. It's also worthwhile to make the circuit and experiment with different capacitors. But there you go. I've heard people say that a picture is worth 1,000 words. Well, it may not be the world's best oscilloscope, but it still did make quite a pretty picture. So while you continue to admire it, I'll be seeing you.